Okay, so in this lesson I want to bring a few ideas together that we've looked at in previous lessons, and specifically I want to look at Newton's laws of motion. Okay, so you can see on the screen there I've got a copy of the blue document that this is stuck into your books, which goes into quite a lot of detail about Newton's laws of motion, but we just need to pick out the important bits. So in your exercise books, if you could write the title, Newton's Laws of Motion. And we're going to start off, not surprisingly, with the first law of motion. Okay, so Newton's Laws of Motion. And it is important that you can quote these laws of motion. Okay, so the first law. And I see no better source for that than to have a look again at the document here. Okay, so you need to be able to quote these laws as stated on this document, but also obviously understand, talk about them, and use them. Okay, so if you could write down an object stays at rest or maintains a constant velocity unless it is acted upon by an external force in your notes, then that would be a good start. And also make sure you make it clear you need to learn that, you need to know that, you need to be able to quote it in an exam situation. So you might want to pause the video now just to get that done. Now, in addition to being able to quote it, obviously you have to be able to use it. So we've got some diagrams here which should be familiar to you because they're of a parachutist, and we've done quite a lot of work on parachutists. And these three diagrams do illustrate what the law, this first law of motion talks about. Okay, so this parachutist here is in free fall. However, from this equation here, we can see that he has reached terminal velocity because R1, which is the air resistance he has experienced due to his speed, is equal to W, which is his weight, and his weight is the effect of gravity on his mass. Okay, so what we can consider at this point the weight to be the force, which is a combination of his mass and acceleration due to gravity. Okay, and he is traveling very fast downwards, but he is at constant velocity. He's not changing. Okay, he's not accelerating or decelerating. So here he is obeying Newton's first law because he is maintaining a constant velocity and is not being acted upon by any other external forces. Okay, the forces have come to be balanced, which is another thing we need to look at again briefly. In this diagram, R1 and R2, now R1 is still the resistance that the parachutist himself experiences, the air resistance, plus R2, that's the additional air resistance of the parachute, is greater than the weight. Okay, so at this point, the parachutist is not experiencing balanced forces. The upward force is greater than the downward force, and we can see that because the arrows, the blue arrows, are bigger than the red arrows, and consequently this parachutist is decelerating. He's decelerating because the forces are unbalanced. Okay, so this object is not maintaining a constant velocity. He's actually decelerating because he's being acted upon by an external force, and that external force is the greater air resistance compared to his weight, which has remained constant. And then finally, once the parachutist reaches a lower terminal velocity than when he's free falling, we end up in a state of balance again. So once the parachutist accelerates, even though he's got a parachute, he will accelerate, but he will only accelerate to a much lower terminal velocity because the additional resistance of the parachute will reduce that velocity, and we end up again in a balanced state. So R1 and R2, the resistance of his body and the resistance of his parachute, are equal to the weight pulling him down. So the size of the red arrow and the sum of the sizes of the blue arrows is the same. Okay, and he is now in balanced fall. Okay, now to illustrate that, we'll go back to our graph that we've looked at a few times now, and we'll just have a look at a few phases of this, and we'll consider these phases in terms of balanced or unbalanced force diagrams. So at this point in the graph here, okay, his velocity starts off at 0, and over a period of 5 seconds it increases to 41 meters per second. So here the parachutist is clearly accelerating, okay, and therefore we could represent that process by, if we use the sort of simple circle to represent the parachutist, okay, he is in the state that we saw on the second part of that diagram. Just go back. So whilst the parachute's not out, he is in this state here. He is accelerating. Okay, so his weight due to gravity is relatively small. Okay, no, sorry, his weight due to gravity is bigger, rather. He's bigger than the resistance due to his body. Okay, so he is accelerating quite rapidly because the effect of gravity is greater than the air resistance. Now, we have seen this previously. Okay, we saw it as part of your TIM task. So these diagrams here were all about representing that. So this is the first part of the journey, and the weight or due to gravity has a greater impact on his movement than the air resistance. So at this point, he is unbalanced. Okay, the forces acting upon him are unbalanced, so he's accelerating. Here is a similar situation. However, the impact of air resistance is greater, but it's still not as great as gravity. Okay, so this arrow is ever so slightly bigger than that arrow. Okay, because he's still accelerating. However, when he reaches this stage in his journey, there is no change in velocity. Okay, so at this stage, he has reached a stage of balanced forces. Okay, so this is the state that we see in the initial picture on our diagram here. Okay, so it is this state here where he's in free fall, but the air resistance is equivalent to the effect of gravity that creates his weight. Okay, the next point on our graph is here where he decelerates rapidly. Okay, and this is where air resistance is more significant, is a bigger force than his gravity, the gravity that's exerted on him, and therefore he's decelerating rapidly. And then here we've got the air resistance is lower because he's slowing down, and here we have the gravity, which is still slightly smaller but not quite. And then the final stage of his journey, he's back to being in balance again because the air resistance and gravity are equal, even though his velocity is much lower. Okay, so we do need to be aware of this feature. Okay, and that sort of brings us on to Newton's second law. Okay, so there's no explicit maths associated with. The only maths that we might start talking about is adding values to these arrows. Okay, we'll have a look at that later. Okay, so at the moment it's quite a descriptive idea, but we do need to start adding some values to those arrows. So if we now need to put another subtitle, the second law. And again, we're going to refer to the document over here. Now, this is a bit more wordy. Okay, again, you do need to be aware of this, but luckily it can be summarized with this equation here. Okay, so in your notes, if you copy that second law down, okay, and write that equation underneath it, okay, because we are going to be using that equation quite a lot. Okay, so if you need to pause the video to do that, then please do so. Okay. Okay, so we're going to go back and we're going to have a look at this diagram, but this time we're going to add some actual values in order to discuss Newton's second law. Okay, so Newton's second law, as you've hopefully already got written down, can be summarized as force is mass times acceleration. Okay, so this is force, and forces are measured in newtons. This is mass, or the mass of whatever object we're talking about, and the mass is measured in kilograms, and acceleration is measured in meters per second per second. That's m/s squared. Okay, is meters per second per second. And we've already seen quite a lot of examples of acceleration in use. Now, one sort of cornerstone of physics is the study of gravity. Okay, we've used the example of a parachutist already, so we just need to say a little bit about that. So we could adapt this equation here, okay, by remembering that the acceleration due to gravity is 10 meters per second per second. It's actually more like 9.8, but 10 meters per second is fine for most calculations. Okay, so that's gravity. Okay, so we can use that value there. So objects accelerate towards the Earth at a speed, that's an acceleration rather, of 10 meters per second per second. Okay, and that's the acceleration due to gravity. So we need to sort of bear that in mind. And so if we take an example of our falling parachutist, okay, and if we take an example here of this force here, okay, so we're gonna look at the force due to gravity if I were to jump out of an aeroplane, okay, which would be quite scary for anybody attached to me, I would imagine. So the force that would be dragging me down due to gravity, okay, here. So I'll just redraw this as a bigger diagram over here. So when I first jumped out of the airplane, the force that would be dragging me to my fate would be 120 kilograms times 10 meters per second squared. Okay, so that force would be 1200 newtons, because when you multiply kilograms by meters per second, we get newtons. Okay, now if I was in that initial phase of flight, at some point during that flight, I might experience air resistance in the region of 400 newtons. So here the force would be 400 newtons. Okay, and we can use this diagram to resolve the force that is acting on me. Now, resolve is a fancy word for saying work out the force that's acting on me. Okay, so I'm sure that you can probably see this, but the force that's acting on me is 1200 newtons dragging me down, and 400 newtons is trying to keep me up. The force of the air resistance is trying to keep me up. So the resultant force is 1200 newtons. Take away the 400 newtons, which of course equals 800 newtons. So we could perhaps redraw that diagram simply as that with 800 newtons. Okay, so effectively I'm being dragged to the Earth by a force of 800 newtons due to the combination of my mass and the acceleration due to gravity. Okay, so this idea of resultant forces is quite important, but given that it only ever involves two forces, and it simply subtraction sum, then that should be reasonably straightforward. Okay. Now, also sort of linked to Newton's second law, occasionally we might be asked to find an acceleration by using an equation that we've seen previously. Okay, so there are occasions where we might use the equation that we could illustrate using this graph. Okay, so you might recall that the acceleration is equal to the difference in velocity divided by the time over which that change happens, that difference happens. Okay, now that's quite long-winded and quite wordy, so we can summarize that with in a true algebraic manner by replacing the word acceleration with a. We've already seen a used for acceleration in the previous section. And then the difference in velocity. Now, v is a good letter to use for velocity, and you may have come across in maths or other aspects of physics that we often use a triangle, which is pronounced delta, and a v for velocity. So delta, I'll just put that here, means change in maths and in physics, and then v obviously means velocity, and then a little t for time. Okay, so delta v is the change in velocity. Now, in many exam questions, the difference in the velocity you find out by looking at two velocities that are given to you, and very often the initial velocity, the start velocity, is 0. Okay, so if the start velocity is 0, then basically the change in velocity is simply the final velocity. Okay, so if you see phrases like an object starts from rest and accelerates to 50 meters per second in 10 seconds, and you may be asked, what is the acceleration? And you will usually be directed to a set of equations, usually on page 2 of your exam paper, but they will be on your exam paper. And basically on page 2, you'll be looking for this equation here. Okay, the difference in velocity divided by time. At first, you might be thinking, well, what's the difference in velocity? Because I'm only given one velocity, 50 meters per second. But the phrase rest or at rest is equivalent to 0 meters per second. So at rest means it's still. Okay, so in this particular instance, okay, delta v, so from our equation that we were looking at previously, so delta v here. So delta v is the difference in velocity, and that would be 50 meters per second. That's the end velocity. Take away 0 meters per second. Okay, so 50 take away 0 is obviously 50. Okay, and then if we were to then place this back into our equation, so we're looking for the acceleration. So that's delta v divided by t. Okay, so we now know delta v. Delta v is, that's a v by the way, is 50 meters per second. T from the question is 10 seconds. Okay, so acceleration is 50 meters per second divided by 10 seconds. Okay, and so 50 over 10 is 5, and the units of acceleration are meters per second squared. Okay, so that's using an equation that you're given in the exam to find out an acceleration, okay, in slightly unusual circumstances, in as much as the object is starting from rest. So if we go back to our graph, that's this part of the graph here, because the object starts at 0 meters per second and accelerates to 41 in a period of 5 seconds. For the sake of practice, okay, so this is 5 seconds, this is 41 meters per second. Okay, so if we put these values into our equation, okay, the acceleration in this particular instance, different example, is 41 meters per second divided by 5 seconds. Okay, and that is equal to 8.2 meters per second squared. Okay, so this equation here, the difference in velocity, very often the difference is simply the final velocity. Although do take care because, for example, in this case here, I recall from the TIM task, the change in velocity is actually 55, take away the 41. Because the change in velocity is the value represented by that line there. And so in this instance, the change is 55, take away 41, okay, which equals 14. So just take care that you are using the right value for difference in velocity, but very often it will simply be the maximum velocity mentioned in the question, because the object will often start from rest. So just be aware of that. Okay. Now we need to have a look now at Newton's third law. Okay, so again, you put subtitle third law. And again, we will go back and have a look at our document that's stuck in your books. Okay, so the third law here, every action has an equal and opposite reaction. Okay, so for this question, we might want to refer to our knowledge organizer. Okay, but I'll do that in a second. So you make sure you've got a copy of that down, because again, you do need to be able to quote that law there. Every action has an opposite and equal reaction. And just briefly mention the diagrams given here. So a crate on a sledge exerts a force on the sledge due to its weight, and the sledge exerts an equal and opposite reaction force on the crate. Okay, so this reaction force is often used to describe when the earth basically is pushing up to stop, in this example, a crate falling through the earth. Okay, so the reaction force as you're walking down the street is the reaction force of the ground underneath you that stops your weight taking you through to the center of the earth. Okay, so it's basically the force of the solid matter beneath you. Okay, so in addition to that example, we've also got your knowledge organizer, which is this document here. Okay, and in the knowledge organizer, we've got a couple of examples. We've got a rocket, okay, pushing exhaust gases backwards, so the gases will push the rocket forward. So if we just take that as an example, we'll go back to the picture there. So in the case of the rocket, we've got the rocket on the launch pad there, which is the best rocket you've ever seen. Look at that. Okay, so when the rocket's at rest, then its weight, okay, is pushing down, preventing it from flying off in the air. Okay, but equally there is a reaction force of the earth beneath it that stops it falling through the earth. However, let's extend this picture here. As the rocket launches, and it exerts the gases leaving the back end of the rocket exert force in that direction, and the opposite and equal reaction is that the rocket starts to move in that direction. Okay, so the thrust of the rocket is in the opposite direction. Okay, as the rocket is in flight, okay, then we have to start worrying about air resistance again. Okay, so the thrust of the rocket is pushing it forwards, or upwards rather, but air resistance, as the rocket gets faster and faster, much like the parachutist, becomes more and more significant. So we will get to a point, as we've discussed previously, where these two forces are the same, and at this point the rocket will be travelling at constant speed, because the thrust due to the gases being pushed out backwards and pushing the rocket upwards, okay, which is adhering to Newton's third law, is being balanced by the air resistance. Obviously, with this being a rocket, eventually it will leave the atmosphere. There will be no air resistance anymore, and therefore the rocket can then start to accelerate to ridiculous speeds. Any sort of spacecraft that travels around the Earth, okay, they travel at many thousands of miles per hour because there is no air resistance, and therefore any small increase in force acting upon them accelerates them quite rapidly. Okay, so that's a good example of his third law. But in addition to the rocket, we've also got the example of the speedboat. Okay, you might recall we had a look at a question on the speedboat a few weeks ago. And the speedboat example, you've got to be aware. Now there's my thing on. So in the case of the speedboat, we've got the boat itself. I shall not be able to draw quite such a exciting diagram with the propeller. There's the water. So as the propeller thrusts the water in that direction, then the opposite and equal reaction of the boat is to travel in that direction. Okay, so that is the boat adhering to Newton's third law, because it travels in an opposite and equal direction to the thrust of the propeller pushing the water backwards. Okay, so that was a very quick run through Newton's laws. Or you can rewatch the video, make some notes, use the knowledge organizer. Okay, this document here, to make sure you understand the three laws appropriately. There are other examples mentioned here that you can have a look at. You can even use the original syllabus, not that gives the all this information in a slightly more formal manner. Okay, but it's never a bad idea to be aware of your syllabus, and make sure that you refer to this document here and read through this, make notes on this, and all the other work that we've done previously. Okay.